Hello, and welcome to another lecture. This lecture will look at non-homogeneous equations, um, and we'll look at the method of undetermined coefficients. So this is section 2.5 in the book, and you can get the book at this URL. Well, the URL is in the description, and you can download a PDF or maybe get a paperback if you want. All right. So what are we doing? Well, for example, suppose that we have an equation like this. It's a constant coefficient equation, but now we have a right-hand side, right? This is not zero. It's not homogeneous. So what do we do with this type of equation? Well, and let's before I get to that, let's write this as let's write this as L of y, where L, that's what we're calling the left-hand side, the operator, right? So we're writing for short, so that I don't keep writing this, I'm going to just write Ly as 2x plus 1, right? Or, when the L might be a bunch of different ones, but in this lecture, it's always going to be this constant coefficient linear operator, something like this. Right, so we have L of y as 2x plus 1. It's this equation. All right, now what we're gonna do is we're gonna consider the associated homogeneous equation. So this is the associated homogeneous equation. Notice that the left-hand side is exactly the same, but we've put a 0 on the right-hand side. Basically, we're looking at L of y. L is the same L as out here. We're looking at Ly equals 0. So that's what we're calling the associated homogeneous equation. Now, the general solution to this guy, to the associated homogeneous solution, is called the complementary solution. So it's the y sub c, and it's going to have some arbitrary constants in it, so that you get the general solution to the homogeneous equation, right? So ignoring the right-hand side. And then what we're going to do is we're going to find one particular, any particular solution, y sub p. Doesn't have to be the general solution. Any solution, however you get it, you don't have to get a specific one, just any solution whatsoever. Generally, the easiest one that you can find, that's the one that you pick. And we call it y sub p. But again, there could be other y sub p because we're looking for any particular solution. Usually you pick the one that's somehow simplest. So you guess it somehow, right? It's essentially what we're going to do today. We're going to do smart guessing, right? And so you find this, some one solution. It's not the solution that you're definitely looking for. I mean, usually you have this thing with some sort of initial value, some sort of initial value problem. So you have some initial conditions. So we're gonna do that after we find the general solution to this guy, right? So to do that, we find some particular solution, and we don't care what its initial conditions are. That's basically the idea. But we can find the general solution to this guy, right? And now we put it together. We set y to be y sub c plus y sub p. Y sub c is the complementary solution that has the right number of unknown constants so that we can solve for our initial conditions. And y sub p is there to get us the right-hand side, but it doesn't have any undetermined constants anymore, right? I mean, it's just some particular solution. And we claim that this is the general solution, right? This gives you, it's not just the solution, it's actually going to give you all the solutions, right? To this equation, to the equation that we're interested in here, right? And it's really because L is a linear operator. So if I apply L to y, it's L of y sub c plus y sub p. So it's linear, so it's really L of y sub c plus L of y sub p, and we know what those are. L of y sub c solves the associated homogeneous equation, so that's 0. Y sub p solves this. It's a particular solution to our equation, so in particular that's 2x plus 1. Hey, that's what we wanted. L of y is 2x plus 1. Why is it the general solution? I definitely get all the solution. Well, suppose that you look at two particular solutions. Any two, like you found them in two different ways, and you found two different ones, right? Let's look at their difference, right? Let's look at L of y sub p minus L of y tilde, right? Which is some other random solution, right? Well, again, by linearity, we get this, and now both of these, now there's particular solution to the original equation, so they're both 2x plus 1, right? So 2x plus 1 minus 2x plus 1, 0. So that means their difference solves the associated homogeneous equation. That means that if I go from one particular solution to another particular solution, the difference is a solution to the associated homogeneous equation. So therefore, if I want any other solution starting from y sub p, I just need to add to it one solution to the associated homogeneous equation. So if I add all of them, right? If I add y sub c, which is the general solution to this, I get all the solution to the equation that I'm looking for, right? This thing. All right, so let's state again as a theorem, right? If we get the general solution to L of y sub c equals 0, and y sub p is any particular solution, so just one solution to L of y sub p equals some f of x, right? Where f of x is some function, then y sub c plus y sub p is the general solution to L of y equals f of x, right? So if we can find y sub p, and if we can solve, we can find a general solution to the associated homogeneous equation, we have the general solution to the non-homogeneous equation. All right. Well, okay, that's great. But how do we find some y sub p, right? So if we have this guy over here, we have to find some y sub p, some particular solution. So the technique that we're going to describe is called undetermined coefficients, and it's smart guessing, right? So we want y sub p such that L of y sub p is 2x plus 1. 2x plus 1 is a polynomial, right? Derivatives of polynomials are polynomials, and actually the degree never grows, right? So this is the polynomial of degree 1. If I take a derivative of it, it's 2. If I take another derivative of it, it's 0, and then I keep getting zeros. So if derivatives of polynomials are polynomials, and if I look at this thing, so I'm getting some, I'm getting a second derivative plus 5 times the first derivative plus 6 times just the function itself. So I'm taking some linear combination of the function and its derivative. Now, well, linear combinations of polynomials are polynomials, and also the degree doesn't grow. So if I want a polynomial of degree 1 here, what I could try is a polynomial of degree 1 in the left-hand side. That's going to give me some polynomial of degree 1 on the right-hand side. But I don't know which one. So what we're going to do, if we're going to try this ansatz, we're going to, as you remember, ansatz is the German word for doing something like that. So we're going to, just guess a form for the solution. It's going to be ax plus b. It's supposed to be a linear polynomial of degree 1, but I don't know what the coefficients are. So a and b are just unknowns, and I want to figure out what they are. So let's plug it into the left-hand side. Well, if we plug this in, right, we get the second derivative plus 5 times the first derivative plus 6 times the function itself. And if we work that out and do a little bit of a little bit of algebra, we get this thing. Or if we do a little bit more algebra, we get that it's 6a times x plus 5a plus 6b. Now we want 6a times x plus 5a plus 6b. We want that to be 2x plus 1. So you want this to be 2x plus 1, right? That's what we want. We want this to be 2x plus 1. Now, that will be true if 6a is 2, because we want 2x, and we have 6ax, right? So let's just make sure that a is such that 6a is 2. And 5a plus 6b, we want it to be 1, right? So we have two equations that we just solve for, and maybe you just work it out somehow, and you get this, right? All right. So if we plug that in, right, plug these guys into our trial solution, our ansatz, we get this particular solution. So we can simplify a little bit and get it to be 3x minus 1 over 9, right? If we have 1/3 and 1/9, those minus 1/9, right? Those are a and b, right? So that's our particular solution. Now, and I'm not going to do that, but you can solve I'll let you do it. You can solve the complementary problem. So that means set the right hand side to 0 and solve the associated homogeneous problem. The left hand side equals 0, right? And we're going to get this complementary solution. So that's the general solution here. All right. Now, to get the general solution to this problem, we just add the two. So we take the complementary solution and we add the particular solution. Okay, and we're done. We have the general solution. All right. So suppose that we had an initial value problem. So suppose that we had the same equation as before, but suppose now that we have some initial condition. So we have y at 0 and y prime at 0. Well, we do exactly what we do normally. We take the general solution to this guy, right? We take the derivative, right? So that we have y and y prime, and we plug in 0 in this case, and we set it equal to these numbers. So 0 is supposed to be 0, so y at 0 is, well, if I plug in 0 over here, I have c1 plus c2 minus 1/9. If I plug in 0 to y prime, I'm supposed to get 1/3, right? So if I plug in 0, I'm going to get minus 2c minus 2c1 minus 3c2 plus 1/3. And so we solve. Do a little bit of algebra, you figure out that c1 is 1/3, c2 is minus 2/9. So I can put those over here, and I get 1/3 minus 2/9. Of course, that we have the y sub p. I can do a little bit of simplification here. Doesn't really matter. That's what it is, right? That's the solution to this initial value problem. So it's the solution to this that satisfies these initial conditions. Now, a little bit of a warning. So don't solve for the C1 and C2 in the y sub c. You have to add the y sub p to it, right? You have to have this guy in there. I mean, and that makes sense. We're solving this this equation. So you want the general solution to that equation. If y sub c is a solution to a different equation, right? So it wouldn't actually work. It would give you some nonsense numbers, right? If you did if you solved for the conditions in y sub c instead of in y, right? In the solution to this thing, right? You want this guy to satisfy these initial conditions. All right. Now, so that was for a very simple right-hand side 2x plus 1, and we tried ax plus b. So what if you have some polynomial that's of high degree, right? Let's suppose that x cubed plus 1, right? You want to try, I mean, a polynomial of degree 3, but you don't want to try ax cubed plus b. That wouldn't work. You have to try the general cubic polynomial. So you'd have to have ax cubed plus bx squared plus cx plus d. So you're going to have 4 constants to solve for, right? Even though this looks kind of simple, but you really need to try this. I mean, it might happen that some of these will just end up being 0, but it also might not. So, all right. So that was for polynomials. Sines and cosines and exponentials are actually similar. So, for example, let's try cosine, right? So, okay, we have a slightly different left-hand side, and a different right-hand side. So cosine 2x. Now, the derivatives of cosine 2x, well, you'll get a sine, and then you get a cosine, and you get a sine, and you go cosine, right? So all those derivatives and their combinations will be combinations of cosine of 2x and sine 2x, some linear combination of that, right? Some constants in front, right? So what we want to do is we want to try a solution of this form. A cosine 2x plus b sine 2x, right? And plug that in and solve for a and b, right? Okay, so let's do that. Right, so you take derivatives here. The derivatives are not too bad. You take 2 derivatives of this, you get this. Take 1 derivative, you get this, and you just plug the thing here. And we want that to be cosine 2x. Okay, so we need to do a little bit of algebra. We just sort of group the cosine 2x together and sine 2x together. So we have this many cosine 2x's and this many sine 2x's. So what we need is for this to be 1 and this to be 0, right? Because there is no sine x on this side, but there is this many sine 2x's on this side, right? And for cosine, we need 1 cosine, right? So we have these 2 equations. Okay, well, that can be simplified, right? And you solve, and you find that a is minus 1/10 and b is 1/5. Just a little bit of algebra at this point, right? So you plug that in, right? You plug in this a, this b, and I already did a little bit of simplification here, and you get that y sub p, right? Some particular solution to this is this guy over here. And so you see that we really did need both the cosine and the sine, right? We have that 1/5 of a sine of 2x in our particular solution. We needed it, right? We couldn't get by with just trying a cosine 2x. All right. Now, exponentials, very similar. If I have L of y is 3x, you try a times e to the 3x, right? So very similar, because it's, its derivatives are still going to be, they're going to be just some constant times e to the 3x, right? So that's actually kind of simple. And we could combine these, polynomials and sines, cosines, and exponentials, right? So if I have something like this, where I have a polynomial times the exponential times a cosine, well, really, I just need to get all the possibilities of all the possible derivatives, right? Kind of the general form of all the possible derivatives. Well, I could get sine, right? So I definitely need cosine and a sine. And the thing in front, this thing, I can keep differentiating as well. I need a general polynomial in front, and I'm going to need a different polynomial in front of the exponential with this cosine, and a different one in front of the one with the sine. So this is my ansatz, right? This is what I need to try. This entire thing, right? Where A, B, C, D, E, F are some unknowns, right? Some constants. Okay, so what you do, you take this sucker. It's going to be a little annoying, right? You plug it into to whatever the L is, right? The left-hand side is some constant coefficient linear operator. So let's suppose that it's a second order, right? So you're just you take the first or the second derivative of this, plug that in, do a whole bunch of algebra. It's going to be tedious. And then what you're going to end up with is you're going to find equations for 6 unknowns that you need to solve for, right? And you solve for them, and then you figure out what those are, you plug them in here, and you have your particular solution. Okay, so it'll just work, right? It can be tedious, but there's nothing too deep about it. It's really, you're just sort of a smart guess. Like, I know it's going to be of this form. I'm just going to plug it in and see where what happens. Now, it almost seems like, well, we now know, at least, for a lot of different right-hand sides, how to solve, right? How to get that particular solution. Well, these guesses don't always work. They mostly work, but they don't always work, because sometimes that left-hand side, that L, that could just eat your guess, right? And give you nothing to work with. Let's see an example of this. So suppose that my left-hand side is y double prime minus 9y, and I'm going to try this e to the 3x. We had, I was saying before, right? So we would want to try, if we didn't really look at the left-hand side, we'd say, well, okay, so I'm going to try a times e to the 3x. And a lot of times, if there was a different left-hand side, that would work. That would be fine. But in this case, what happens is the following. If I plug that in here, right? So I just, if I take 2 derivatives, I'm going to get 3 coming down twice, right? So I'm going to get 9. So I'm going to get this, and then I have minus 9 times a e to the 3x. I mean, that's 0. There's no way, no matter what a I choose, it's always 0. There's no way I can make it equal to e to the 3x, right? I can't solve for a, right? Well, every a will just give me 0, because this thing is in the complementary solution. It is a solution to the associated homogeneous equation. That's the problem, right? So to save work, because you generally want to find the general solution to something like this, so you should always first compute the complementary solution, right? And then once I compute the complementary solution, I notice that this guy is there, right? So this is just not going to work, right? There is a duplication between my guess and my complementary solution. Okay, so what to do? So this is not going to work. I mean, if you change this just a little bit, if it was minus 8y, it would work. It'd be fine, perfectly, right? You could try this, but now we can't. Well, it's something similar like we did before. Well, we just multiply by x, right? So multiply the guess by x. So we're going to have ax to the 3x, right? Let's see why that works. Well, so if I do y prime, well, you're basically, from this, you use product rule, right, when differentiating. And so you get your a to the 3x out here, and so basically you get these 2 terms, right? Now if I differentiate again, I'm going to get this. It takes a little bit of calculus and algebra, but that's what it is, right? And you can see that I have sort of more to play with, right? When I plug that in, of course, I don't want any x e to the 3x on the right-hand side, but hopefully I can make that work, right? And hopefully I can get the some e to the 3x on the left-hand side, so that I can set it, I can solve for a. So all right, so let's plug that in, right? So if you plug that in, so you get this, right? You get y double prime. That's this thing, and then y double prime is this thing, sorry. And then I do minus 9 times this thing, right? So I have this, minus 9 this, right? So I'm going to get 6a e to the 3x. Oh, the x e to the 3x vanished. Great. I don't even need to worry about it. And a, I can now choose to be whatever. So, all right. So if I do that, I want this to be e to the 3x, right? That means that 6a is supposed to be 1, so a is 1/6. All right, so the general solution is, well, I just take my complementary solution, add my particular solution, which is, this guy, so with the x, of course, right? Where a is 1/6, right? So this is my particular solution. Okay, great. So we've found the general solution to this, right? Even though this guess didn't work, right? So we just have to modify our guess a little bit. Now, multiplying by x1s may not be enough. Yeah. So sometimes you need to do more. When we're talking about second order, it's going to be enough to either multiply by x or x squared. If it would be higher order, you might have to do more. But so let's see where that comes up. So suppose that we have this left-hand side, and again, e to the 3x on the right-hand side. Now, the thing is, now if we find the complementary solution, okay, there's that e to the 3x. So I say, okay, I can try x e to the 3x, but then I notice, well, that's in my complementary solution as well. That's gonna also get eaten by the left-hand side, right? Because that's how we dealt with doubled roots. This thing, we're gonna get a double root for the if we're trying e to the rx, right? So we're gonna get the double root 3, and so we're gonna have to, like we get e to the 3x and x e to the 3x. Well, you just multiply by x again, right? So this doesn't work because it doesn't get rid of the duplication, but we just multiply by x again, right? So we take this, multiply by x, we get ax squared e to the 3x. And let's try that. That's a little bit more annoying to take derivatives of that, but yeah, it still works. And in the end, you just, have one, one constant here to solve for. So it's actually, that's not so bad. So basically the idea is keep multiplying by x until the duplication is gone, but no more. Like don't just always multiply by x squared. That won't work. All right. Now, what if the right-hand side is a sum of these things? Sum of different right-hand sides. Well, what you can do, and this will apply to all the other techniques as well, you could always solve this equation. So let's suppose that you find a particular solution u that solves this, and particular v that solves this, right? So basically, we just split up the right-hand side into the two parts, and then we're going to use linearity. So if we set y to be u plus v, then ly, well, that's going to solve our original equation, because ly, that's L of u plus v, but L is linear, so it's L of u plus L of v, and L of u is 2x, and L of v is cosine x. All right, so that's undetermined coefficients. Next time we're going to look at another technique to solve non-homogeneous equations when you have the right-hand side. I mean, when did undetermined coefficients work? They worked because I had the right-hand side such that if I differentiate it just like finitely many times, basically, I get something of the same form, right? I can find sort of a general form for all the derivatives of the right-hand side. But it might be that the right-hand side is something, and that's actually kind of the that happens a lot. When the right-hand side is some function, and you keep differentiating, and you get something, it always has some different form. So you can't just write a general form for it, right? Each time you take a derivative, it looks completely different, right? So you cannot write down some linear combination of all the possible ways the derivative looks, right? Okay, so we're going to look at that next time. All right, so see you then.